In this video, I'll talk about how to determine which particular molecule will have a higher boiling point or will have a higher solubility in water based on the intermolecular forces. So the main type of compounds you will be seeing in there would possibly would have an aldehyde functional groups, a ketone, and you could also see alcohols here and there. So your boiling point and the solubility has to do with what type of intermolecular forces can be made in those particular compounds. So I'm not going to be writing the intermolecular forces on the full here because that's just going to be time consuming, but I will write down based on these acronyms. So for example, if something is making an hydrogen bonds, I'll write down A. So A stands for the hydrogen bonds, and then let's write down B. That's going to stand for that it's making a dipole interaction. And then C is going to be dispersion. Now remember, every single compound, regardless its type, will have the potential to make dispersion forces. Now there will be time when one compound can make a greater amount of dispersion forces or a less amount of dispersion forces. But either way, they are capable, every single compound is capable of making dispersion forces. So I can probably just say, okay, well, every single compound is going to be making dispersion forces. So I can write down C for every single one of those. But let's try one pair at a time. So on this first pair, this is going to be making dispersion forces just because every compound can do so. But then also, if you have a longer carbon chain, carbon and hydrogen chains, they are capable of making stronger dispersion forces. And if you look at the difference between this left compound and the right compound, both of them possesses carbon-oxygen double bond, which we had said earlier that it's going to be polar. So as a result, it's going to be making a dipole-dipole interaction. So this will be making dipole-dipole interactions, and the one on the right side will also make the dipole-dipole interactions. But then, what's really the difference then? I mean, both of those are making the same type of intermolecular forces, and none of those will be able to make hydrogen bonds because that's, remember, the criteria for hydrogen bonds that hydrogen must be directly bonded with either fluorine, oxygen, or nitrogen that you do not see in any one of those compounds in question A here. However, the difference really that you're going to have is just the carbon chain. Like if you look on the left side, you have a little bit of longer carbon chain here. You got two carbon set here, and you got only one carbon on the right side for this the right molecule here. So as a result, I can say that the compound on the left side will be making a greater amount of dispersion forces, or I can say they will be making larger dispersion forces. So as a result, if everything is the same and you're just trying to figure out, okay, who makes a greater amount of that particular type of intermolecular forces, that would have a higher boiling point. So this compound will have a higher boiling point. But now, when it comes down to the solubility, remember, for the solubility, it's not really the boiling point. It's not really the greater amount of dispersion forces, but rather it's the least amount of dispersion forces. Because remember, water is polar, so you want to make sure the molecule can make dipole-dipole and hydrogen bonds to the greatest amount. Now, I know both of those cannot make hydrogen bonds, but then both of them are making dipole-dipoles. So then what's the third criteria? To dissolve something in water, you want to make sure it's making the least amount of dispersion forces. So the compound on the right side is the one that's making less amount of dispersion forces. So as a result, it would have a relatively higher solubility in water. So that's how you're really going to be running all of those down in terms of finding the solubility and the boiling point. So first of all, go ahead and figure out what type of intermolecular forces they're going to be making, and then based on that, you can answer those questions. So let's try this B here, and maybe it'd be a good idea if you want to pause the session and try to do this on your own and see if you get it right. Now, let's say I have On this second one, this is an aldehyde function group. So I know they can make C, which is the dispersion forces. But then in addition to the C, let me change the color here. It also have this carbon-oxygen bond, which is polar, so that means they are going to be able to make dipole-dipole interactions as well. So B and C in there. Let's look at the molecule on the right side. So again, it's going to be making C because every molecule are capable of making dispersion forces. And then I'm looking at a carbon-oxygen bond, which is polar, so that will be making a dipole-dipole as well. But then you also see that this oxygen and hydrogen are directly connected with one another. So as a result, it will be able to make hydrogen bond as well. So if you see like hydrogen bond being made and dipole-dipole being made, then your dispersion forces are going to be not that much crucial in those cases because you try to go for the strongest intermolecular forces when the molecule have a roughly same size or similar sizes. So in this case, I can say since I'm making hydrogen bond on the molecule that's on the right side, that's in a stronger intermolecular force that would have indeed a higher boiling point. But then now let's come down to the solubility in water. So when you are trying to design the solubility in water, water itself makes hydrogen bonds. So you want to make sure you have a molecule that is capable of making the hydrogen bonds and its least dispersion forces. But in both of those cases, they are going to be making the dispersion forces, but the one on the right side is capable of making hydrogen bonds. So as a result, it would also have higher solubility in the water. So that's how you really want to be looking those down. If you see a compound that is making hydrogen bonds and the other compound is just making dipole dipole, the one that's making hydrogen bonds will be more soluble in water and will also have a higher boiling point as long as they are similar in sizes in terms of the number of carbons and hydrogens. You can have a minor differences in the numbers, but you can't really compare a compound with, let's say, 3 carbons and another compound with 10 carbons. That's going to be a little bit hard to compare with the different types of intermolecular forces being made. Let's look at this next one here. So C, we have only carbon hydrogen. So this guy actually, since it does not contain any polar bonds, it's going to be able to make only dispersion forces, nothing else. Now, the one on the right side, I know it's going to be able to make dispersion forces just because every compound makes dispersion forces. And on the top of that, you do have a lot of carbon and hydrogen bonds only in there as well. But then along with that, you also have a carbonyl there. That means it's also going to be able to make dipole-dipole interactions. So I want to go ahead and write down B here as well. Now, for that reason, since B is going to be in a stronger intermolecular force, and you can also see here the size of these molecule is roughly the same. It's just a difference in the presence of an oxygen. But if you look at the overall size, it's not a big of difference. So since I'm making making dipole-dipole interactions on the one on the right side, this will be having a higher boiling point, and it would also have higher solubility in water. Okay. Let's look at this next one here. So when I'm looking at this next one again, I'm not really seeing much a big difference in terms of the sizes here. So I got an cyclohexane ring in both of those cases, but the one on the left side will be making dipole-dipole interactions because you got a carbon-oxygen bond here, and then you obviously going to be making dispersion forces. The one on the right side, I have an carbon-oxygen bond, so yes, for sure, dipole-dipole interactions. But then also remember it's actually got an OH bond in there. So this hydrogen, since it's directly connected with the oxygen, it's capable of making hydrogen bonds. So A is also going to be there, and you certainly have a C in there as well. But since the compound on the right side is capable of making hydrogen bonds, it would have higher solubility. Everything else is kind of the same. Both of them are making dipole-dipole and dispersion forces, but then since the one on the right side is capable of making hydrogen bonds, the hydrogen bonds are the strongest intermolecular forces out of those three. So this will indeed have a higher boiling point, and since it's making hydrogen bonds, it would also have higher solubility in water. So this is how you really run those down in terms of the solubility and the boiling point.